Thank you for coming, James. Hello, everyone. We are now having James Staley that are going to show us his work, his current work. James is a PhD candidate in human-robot interaction at Tufts University AABL Lab. He has been working on robotics and interactive AI on and off for the last decade. On today's session, we're going to have some interesting topic about reinforcement learning on robotics right now, like LFD. LFD is learning from demonstration. It's currently one of the how can I say it? Some exciting visuals for our reinforcement topic right now, for reinforcement learning topic. And we have several topics that could be discussed as well, like diffusion policy, DP, implicit behavior cloning, IBC, and some like MBRL, model-based reinforcement learning. And this is going to be a pretty interesting talk. So, James,
I hope so. Right. I'm James Staley, a PhD candidate at Tufts in the ABLE Lab. It's a human-robot interaction lab. And today we're going to talk, thanks for the introduction. And today we're going to talk about systems that can learn from all kinds of demonstrations, which we've acronymed as GOAT for gains on all trajectories, because we want to be able to consume all kinds of data. So first off, we all want robots in the homes, and we want robots to be able to learn from human beings. The first reason for this is that we're probably going to have novel tasks and behavior customizations. It's unlikely that even with the most large out-of-the-box model, we'll be able to handle every task a person might want a robot to do. Especially when you consider that people usually want work done in a certain way. So it's not just, can you do this task as a binary? It's, can you do this task the way that I want you to do it? So we're probably going to need some kind of like lifelong learning, in the home learning for that reason. Another reason is that it's really the only option for non-technical operators. So my mom can barely navigate her phone. She doesn't even really use email. And there's no way that she would be able to give a robot information about how to do something or what to do outside of like an interpersonal modality, like a language model, or we're talking about demonstrations today, or demonstrations. So it's really the only option for non-technical operators. You can't interact with the robot through code, or even in a lot of cases, even through like a technical interface. And finally, we can think of learning from demonstration as sort of being an alternate to reward functions. In reinforcement learning, we would get a reward function that would guide the agent's behavior over time. But an alternate way to deal with this is to use imitation learning or learning from demonstration, where we don't end up with a reward function that's hackable. Like if a reward function gives you dense reward over the task space, you've probably heard of reward hacking. And that's just to say that the dense information can actually be bad for you because it can lead you to non-ideal behaviors. So one way, there's a lot of work, really good work being done on reward functions, but another way around that is to basically just sidestep them, use either a purely sparse reward or imitation. So at the end of the day, we just want robots to do what humans want them to do. And luckily, human demonstrations help us address another problem that's really big in robotic end-to-end learning, which is that robot data is very expensive. Just making sure the slide updated. Live robot data is arguably the most expensive kind of data, so we really don't want to waste any of it. We want to be able to use all kinds of robot trajectories and demonstrations to train our system. So, you might have a data set that produces an excellent, well-tuned, narrow, single-task behavior that you want to include. You don't want to lose that. So we really want to be able to grab from neural networks, open source data from the open data community and locally, things that are trained on ML algorithms, maybe even like random walks, like structured random walks, classical robotics, and demonstrations. And so this is a way to get around this expensive problem. We just have much more data we can pull from all sources, and we can learn a little bit no matter where what the source of the data was. And the reason we really care about that and why we need to focus in on demonstrations here is because when we actually collect demonstrations from real human beings, we get trajectories that look like this. They're messy, they go all over the place, they're multimodal to say the least. And these demonstrations are taken from a recent in the wild data collection we did in the Tufts atrium for a shelf restocking task, which we'll talk a little about at the end. And one question that we're interested in is what can we do with this information? So how can we use messy human demonstrations to help robots learn without bespoke post-processing that depends on the task or the demonstration? Like the ideal goal would be just that you had a non-expert user that was non-expert in the input modality, like the Xbox controller or kinesthetic teaching, give a demonstration and be able to pick up the useful information from that demonstration without being hampered by the fact that it's not ideal because the person has never used an Xbox controller before. So we're going to first look at a method of learning from demonstrations that doesn't try to learn the human's policy, which is imitation learning does try to use the human's policy. And then we're going to look at whether this method and a representative set of imitation learning methods learn the same way from demonstrations that come from trained ML models versus demonstrations that come from human beings. Because as we'll see, human beings and trained ML models output different kinds of demonstrations. So first, we're going to talk about this paper that was at Reinforcement Learning Conference last year, Agent-Centric Human Demonstrations Train World Models, by myself, Shivam Goel, Yash Shukla, and my advisor, Professor Elaine Short. Just to set us up, we're talking about Markov decision processes, where an agent takes an action to influence a state transition and receives an optional reward if we're doing reinforcement learning. We have state, S, actions A, a transition function that describes how an action transitions between states, a reward function that's going to appear in reinforcement learning where we get a value of a state or state action pair, a policy that looks at the current state and takes an action, and then a value function that estimates the value of the current state. If we're doing, again, all the stuff about the reward function and the value function is specific to reinforcement learning, but the MDP that talks about the transition of the world, that is valid for both the reinforcement learning setting and the imitation learning and learning from demonstration setting. So end-to-end reinforcement learning takes a very long time and a lot of data, but guidance from a human teacher can substantially speed up that learning. It's used in imitation learning methods that, for example, use supervised learning to directly learn the human's policy, like in behavior cloning, learn discriminators to distinguish state actions that come from demonstrations from those that don't, as in adversarial learning, learning a dense reward function from scalar feedback or preferences, as in tamer or preference learning, or learning an energy function of the demonstrations for continuous control, as in diffusion policy. So these are all ways that we can try to pull information from a demonstration and use them to learn a policy about how to act in the world. But, and imitation learning is so attractive because it's actually pretty easy to specify a task's goal. It's sort of easily describable as a world state, like if you want a hot cup of tea, that can be described to the robot as sort of a mug of steaming water with a tea bag in it. That goal state is much easier to describe than the path that gets you to the goal state, even if that path has, there might be state bottlenecks in the path, and there might be like an enormous state action space, and that's why we want imitation learning to speed up demonstrations. But it is easy to specify the goal, which is nice. Unfortunately, learning human demonstrations is very hard. So while these methods can show rapid speedups in learning, actually estimating a human's behavior distribution or value function using only limited state action coverage is difficult. In addition, human demonstrations are not as Markovian as we want them to be, and so these methods frequently fall short when we apply them to real-world distributions. So we tried to take a different approach, and we tried to say, What happens if we apply our demonstrations to just train the world model part of a model-based reinforcement learning system and not care so much about trying to train the behavior policy? So basically, can these human demonstrations benefit learning overall because they represent how the environment works, but we don't necessarily want to do something where we're mimicking human behavior. So in other words, we're going to use our demonstrations to train a world model, and then we're going to let the world model train the agent as normal. So we use Dreamer v3, which is a state-of-the-art auto-regressive world model, and we show it demonstrations that train its world model, which then train an actor-critic learner from those world models embedded demonstrations. Oh, sorry, I see that there's no takers. The actor-critic is going to do policy learning within the world model, and the world model is going to learn how the environment and the task works from the demonstrations. So in this setup, the demonstrations are not used directly to train the policy, even if the policy sees snippets of them. We're training the world model's prediction and transition functions so that it can predict when the environmental reward is going to happen, and it can tell how the environment is going to change based on those states and actions. So we have this relatively simple algorithm where we're just going to, we minimally alter Dreamer training. After a period of initial random exploration, we collect an episode of demonstrations using Xbox controller. We then insert human interaction periods into the training evaluation loop until we've collected our target number of demonstrations, after which Dreamer just trains as normal. I wouldn't worry too much about the specifics of this algorithm because since this paper has been published, we basically did an even simpler thing, which we took the demonstrations ahead of time and we just dumped them into the replay buffer. And that works exactly the same. So it is not critical at all that the human is sort of like in the loop during the learning period for this work, although that does have advantages elsewhere. We tested it on 2 simulated tasks, PinPad 5 and Memory Maze. PinPad 5 is a long horizon, sparse reward task where a pixel agent has to step on 5 pads in the correct order. And Memory Maze is an exploration and memory task where an agent has to find state-dependent goals. Both of these tasks require many steps between rewards. They give image observations. We're in the domain of discrete actions right now. And while PinPad is fully observable because it holds this history on the bottom left, Memory Maze is not fully observable, and so they require different strategies, but they're both these like long horizon pure image tasks. And we compared Dreamer with demonstrations to Dreamer without demonstrations. We have a behavior cloning baseline and a PPO baseline with and without reward shaping. So in the PinPad 5 environment, a relatively small amount of human guidance leads to attaining 50% of the max environmental reward about 6 times faster on average than pure Dreamer, and attains 90% of the max reward in 8 of 11 trials, while no other baseline reaches 90% of max reward within the training window. In addition, all 11 Dreamer trials with the demonstrations achieve 50% of max reward, while only 3 of 10 Dreamer trials without demonstration do. Our PPO and BC baselines for this paper could not achieve these sparse rewards, so we leave them off these charts. But basically, that's just to say that when you put demonstrations into Dreamer, it learns a lot faster and it learns a lot more consistently. We split out these results by the number of demonstrations. So even a single action, or sorry, even if a single full episode in blue is enough to substantially improve performance. But of course, as you get more demonstrations, you have better performance and reduced variance. If you're curious about the left side of these charts, these like spikes on the left, that's the human interaction phase. So like the human comes in right at the beginning. We're controlling right in the environment, so that reward shows up. But then the rest of it is just training as normal. Memory Maze sees similar improvements, attains 50% of the demonstrator's max reward in 4 times fewer steps. The results are less stark in Memory Maze, possibly due to the randomly generated environment. and also the lack of a fully observable environment. But it does still help learn this like general strategy about exploring the maze and finding the goals. So why? We're going to speculate a little bit about several reasons for this strong effect. And first, in sparse reward tasks, human demonstrations produce structured exploration that the world model would not otherwise experience until much later in training. So the model gets to see these deep trajectories that go from the initial state distribution to the goal. And obviously that is much better than having to randomly find those trajectories. So that's going to shorten time, of course. Second, we are resilient to imperfect human demonstrations. Other imitation learning methods might incorporate useless or counterproductive human behavior because they're just trying to match the human's policy. So if the human's policy is not great, or if the demonstrations have a mix of quality, then the imitation learning algorithms will pick up that non-ideal behavior. But since dreamers from demonstrations' effect on the agent's policy is indirect and it occurs through the world model, any useful information present in the trajectories can be incorporated into the world model. So as long as the demonstrator is able to drive the agent to its goal, it should benefit the world model's understanding of the task, no matter how bad the demonstration is. And finally, the way that dreamer actor critic training works is you have the world model is learning from the real data that is in the replay buffer. But the actor critic, we're going to take a snippet of real world trajectory, which on this image is in white. Oh, sorry, this is not a note taker. Let me see. Right, so I'll take this question. Basically, based on how does the timing and amount of human intervention affect the learning process? Right. So in this, the timing of the human intervention doesn't matter very much, but the amount will. More data is better. Like PinPad is a small environment, but if you have a lot of varied human demonstrations, you'll get better at your task. There's this great approach that's called data augmentation. It's abbreviated as Dagger, and there's a whole series of work on Dagger. And Dagger does this really wonderful thing where the human, the newer versions of it, the human can opt into controlling the agent at any time. So like, it's one thing to basically take a bunch of demonstrations. You go from your start state to your goal state, and there's variance how people do that, right? But then as a reinforcement learning model learns, like you want to be on policy learning and reinforcement learning because you can get sort of like the wrong idea about what a valuable part of the state space is. And so you have to like sort of wander away from where you want to be to learn that that's wrong and then correct it. And what Dagger does is it says that when you wander away, the human can basically tap in and drive the demonstration back to the goal. And it works really well because like, in addition to having all these great demonstrations that take you like sort of directly from start to goal, you start to be able to correct where the policy actually is, like what the policy thinks it should be doing. The human can come in and say like, well, that's wrong, but it's not enough to tell you that it's wrong. Here, I'm actually just going to show you how to get from what you think you should be doing to what you should be doing. So that's a way in which like, while this approach, the sort of like timing doesn't really matter, there's other approaches for imitation learning and learning from demonstration where timing is much more relevant and fruitful to like have a person standing there. And there's all this great work in human robot interaction that's also about like when the agent should interrupt the person so that the person doesn't have to like attend to them the whole time. But we can talk about it a little bit more later. Yeah, I mean, demonstration amount matters more, but timing matters depending on the method, I guess is how I would summarize it. Did I just mess up my sharing? Or can you guys still see everything? Okay, I think you can still see everything. Okay. Sorry for that. Let me answer more questions generally at the end. So, right. So I was talking about Dreamer. So this white trajectory that we see, this is like real world data. This is like what the demonstration is. And the way that actor-critic training works is it takes each of these real world states that exist in the replay buffer, and it does a forward unroll of the imagined states based on the actor's current policy. So the actor-critic is basically always training in imagination space, is one way to say it, like in these forward unrolls that don't have, that aren't corrected by real data. And then when you run it, you take the most up-to-date embedded representation and use that to ask the policy what you should do. But the fact that it trains like this means that the human demonstrations are sort of like extra potent, because we're going to be training on these forward unrolls that come from a scaffolding of the human demonstration. So like, we're going to sort of like be densifying our training trajectories around this human demonstration. And that ends up just being really potent. And it's one reason that we think we see such a strong effect. Yeah, just to lay that home, these are the loss equations for the world model. We have our prediction loss, where we're going to try to be able to accurately predict our next state, the reward, and whether the episode will continue. And then we have these two dynamics and representation loss that's going to try to keep our prior prediction of the next state and our posterior prediction to be close, basically saying that we want our imagined prediction to be close to and representable and correct. And one thing, the reason I'm pulling these equations up are just to show that there is no, while there's this like sparse reward prediction in this prediction equation, loss equation, there's no sense of what should happen. Like, there's no value function, and there's no time, time backed up value. So while you're trying to predict the sparse reward, you leave all of the estimations of value over time to the actor critic. So you have this like nice separation of saying that the world model is saying what can happen, and then the policy is saying what should happen. And those are like separate and distinct. Where for imitation learning and learning from demonstration, you are learning them jointly, basically. And you're saying like, I need representations of the world at work, and I also need to be following the human's policy. I should be doing what the human was doing, which gets you into trouble if you don't have like super clean data or the human is not perfect. Great, so in summary, we use demonstrations to train a world model instead of approximating a human policy or value function. We learn faster and more consistently than with our baselines, which admittedly, I think we could have picked better baselines for this paper. And training a world model is an alternate way to use the incredible and valuable information that is in human demonstrations. So that is the first paper that I'm going to talk about. Let me just see if there's anything I can take right now. Thanks. Yes, proactive interventions. Love that. You could definitely do that with the Dagger style systems. Why are you considering regularization and loss function? Would that help in learning better policy? I think it regularly does. Is there another form of regularization in the Dreamer update? I would have to check the specific code. There's regularization for the actor critic, but I'm not totally sure what the regularization is for Dreamer v3. There's a couple great open source repos. There's Danager Hafner's, who the original author is, and that's a TensorFlow repo. And then I forked a PyTorch version that was easier to sort of like bring human interaction into. But I'm sorry that I can't answer this question right now. I can get back to you later. Cool. So now we're moving on to in-progress work, which is we want to do a more thorough comparison with imitation learning algorithms. As I said, the baselines in the previous one didn't really get into that. It was more about like showing where Dreamer is good with demonstrations. And we're also interested in this question of whether model learning is dependent on the process that created the demonstrations. So like, getting back to this earlier point that's saying we want to use all the data we possibly can, do you learn the same way from a set of human demonstrations as you do from a set of converged model demonstrations. So we're in a similar setup. Imitation learning research does not usually distinguish between demonstration source. So researchers will say they trained on model-generated demonstrations or human demonstrations, but they don't compare the two, and typically don't comment on the effect of using one over the other. Excuse me. And this is worth investigating because AI demonstrations are typically Markovian. The next action depends on the current state. And even if we expand our understanding of state to like a context window, as is used in transformer-based models and diffusion, the window kind of becomes our Markovian state. There's a lot of argument on the internet about whether a transformer context window is a Markovian state, but I think it's fair to say that a windowed state is more Markovian than a human being is. Windows have been demonstrated to be helpful in dealing with the non-Markovian aspects of human demonstrations, like pauses. But a human being has something else entirely going on, which is that like their demonstrations might contain what's called temporally correlated noise or confounding noise, which like another way to think about that is that, if a person is giving a demonstration and they pause, that actually might not have anything to do with the state of the task. Like humans are complicated. A person that's having a bad day or is exhausted or just had a bad conversation with their significant other, they might just lose concentration and think about that for a second while they stop their demonstration. They might stop at some point to sort of reevaluate what's going on. And those are not dependent on the task. They're dependent on the human being, which of course, until we get much scarier sci-fi, that's going to be completely unobservable. So there's a reason to consider that the human and the AI demonstration might end up being fundamentally different in a way that can show up in imitation learning. So we have two questions that we're looking at in this work. Are imitation learning methods sensitive to the source of their demonstrations? And building on our work from human demonstrations, is dreamer from demonstrations sensitive in the same way? So we're going to test on two simulated tasks. We're actually going to use PinPad 4 just because we wanted to speed up training, and push T, which is a standard task for diffusion policy. We're using image observations for PinPad, and then we're going to use image observations in our agent position. PinPad takes discrete actions, push T takes 2D continuous actions, and they both give sparse reward. Push T, if it isn't clear, the point is to push the T over the green T. The goal configuration is the same in every episode, and the T is started in a random location. So the training procedure is a little weird here, so just to spend a moment on it, we're going to start out with a set of human demonstrations, because that's, realistically, you are either training a model from scratch or you're using human demonstrations. But of course, you can't start with trained model demonstrations because the model has to be trained and come from somewhere. So we take the human demonstrations, we train a policy, we then use that trained policy to output a set of model demonstrations, and then we train our models on those demonstrations. So blue is going to be algorithms that are sourced from human demonstrations, and red is algorithms that are sourced from trained model demonstrations. And then we take the most performant model demonstrations after the red step. So in this example, we chose two imitation learning baselines, VMAL, which is an image-based version of generative adversarial imitation learning, where it's adversarial learning. So we're training a discriminator to detect state actions a discriminator to detect state actions that come from the real demonstration distribution versus those that come from a generator. And then when that converges, we can use the generator to generate good state action pairs that are ideally from the demonstration distribution. We also are using behavior cloning, which is a contrastive method that uses an energy function to generalize better than just vanilla behavior cloning. And in this environment, we find this interesting relationship, which is that in the blue, we see our performance from training on human demonstrations. And our imitation learning methods are limited to our human performance, which is this dotted line, which makes sense because they're trying to copy that policy. But we see that Dreamer can exceed human performance because it's using reinforcement learning. And it can take those demonstrations, takes the information from them, and then train a much better policy. But what is also interesting here is that when we go back and use the converged Dreamer demonstrations, so we train this blue line that's up top, and then we take demonstrations from the resulting policy and use it to retrain all our baselines, everybody does phenomenally, right? So only Dreamer does very well with both AI and human demonstrations, and all our imitation learning policies are limited by the human demonstration, and they do much better with the AI demonstration. Sorry. In push T, we see a similar pattern. We are pulling this training from 2 different repos, which is why I apologize for sort of like the spikiness of some of the trials. Instead of VMail, we're using Diffusion Policy for the continuous action space, since it's state of the art and is used frequently on this task. And again, Dreamer from demonstration does the best. It performs similarly with human demonstrations and its converged model demonstrations. In this task, behavior cloning really can't generalize from the small number of demonstrations we gave it per trial, which is like around 100. So it does very poorly. It's down here in blue on the bottom with the little tiny spikes when it occasionally gets a little something going. Diffusion Policy does the best with human demonstrations. Oh, sorry. And then above this in orange is, Diffusion Policy on the AI demonstrations, and it does much better. We think that's probably because they're Markovian. We see that Diffusion Policy, it does the best with the human demonstrations. That's again in blue. And it does much, much more poorly with the Dreamer demonstrations, which is down here in orange at the bottom. That's interesting because it's the opposite relationship than behavior cloning. Implicit behavior cloning was benefiting from the AI demonstrations because they're more Markovian, while diffusion policy is hurt by the AI demonstrations. For diffusion policy, we actually tried an additional step, which is we took the output of the blue diffusion policy model and retrained it just to see how it does on its own demonstrations, and that's what we see in pink. So it has reduced performance because the input data set is worse, but it doesn't do it. It produces demonstrations that look more like human demonstrations, we think, because it doesn't do so poorly as it does with these AI demonstrations that come from Dreamer. Right. So another way to look at these results that might be a little bit easier is just by the episode reward, where we get a sparse reward at the end of the episode, but we retain the overlap reward as a way to sort of like estimate what the policy is looking at. And we see that, on the far right, we start out with the black human demonstrations. That's just done by the paper authors. We're all insider experts who are pretty good at the task. Although it's actually on the 96 by 96 image resolution, it's pretty hard to get the successful trial here. So even though we have really high reward, we only hit the success rate within the time window 86% of the time. And then going from right to left, implicit behavior cloning does poorly, but with both human and AI demonstrations, it can sometimes meet the success condition on the Markovian AI demonstrations. Dreamer from demonstration gets high reward and high success rates. And again, interestingly, diffusion policy is extremely effective at picking up the human demonstrations and the demonstrations produced from its own trained model. So it gets this high coverage reward that you see on the left, but it can't learn from the Dreamer demonstrations, and it has low success rates even when it has high reward. So the chart on the bottom shows that, and it says that Dreamer from demonstration has these really high success rates that are up above the human success rates. But diffusion policy, even in the best case, is only hitting 55.8% success, even though its reward is really high. It's like it knows, it can see enough about the behavior that it can mimic it. But since it doesn't have this additional reward signal, it can't improve beyond that. And so it's limited to just sort of being able to do as well as it can on the human demonstration. And then since the human demonstrations aren't perfect, it doesn't learn a perfect policy, and it can't get any better than that. Yeah, and one thing to sort of reiterate here is that while there's a performance gap by demonstration source between both of the imitation learning algorithms, diffusion policy and implicit behavior cloning, the gap is not in a consistent direction. So IBC does better with AI demonstrations, and DP does better with human and its own demonstrations. This is evidence of two things that we really are trying to get into this paper, which is that practitioners shouldn't treat AI demonstrations as human demonstrations. Like, you know, they're not the same. And so at least explicitly stating what's going on in the papers is really important. And even better, providing examples that come from both sources would be a better way to present results in imitation learning. And two is that researchers shouldn't treat all AI demonstrations as being the same. That is, all AI demonstrations that come from different trained models may have different effects on learning. So, yeah, these are both sort of our conclusions to give to the community. Finally, we went and did an in the wild data collection just in the Tufts atrium, where we collected a bunch of these demonstrations on the shelf restocking task. These results are in progress. We have to finish training the world model end-to-end section, but we have continuous actions, just the X, Y, Z, yaw, and gripper commands. We have image observations, and then we have images. Yeah, and then we have the state observation of the current position of X, Y, Z, yaw, and the gripper. And the task is to lift the can up, put it on the shelf, and then slide it into contact with the shelf with the can that's there. And it's hard because you can't put the cans right next to each other because of the gripper. So you have to put the can down, reorient the arm, and then push it as a sliding motion. So it was an IRB approved study. It's a JCO Gen 3 Lite arm. The people, most of which are naive users, are using Xbox controllers. We got 60 participants over 3 days, 113 usable demonstrations, and 111 successful demonstrations. And just to show you sort of why model and human demonstrations are different, this is a very good participant. This is about as good as we can expect from a participant using the Xbox controller. You still see all these pauses and sort of like non-ideal spots, but that was great. That was super great. And now here's another participant who they will be successful in the task, but they spend a lot more time sort of like figuring out what's going on and what they should do and correcting for their own mistakes. And so if you want to be able to use both of these participants' data, which you do, without having a pretty resource intensive step where you go in and clean up demonstrations, you kind of have a problem with imitation learning approaches where these two videos are coming from, they're both instances of diffusion policy trained on that data that I just showed. I cleaned up the data a little bit just by like excluding the longest trials and by limiting getting rid of the zero initial actions, any zero initial actions. But the success rate is low. I mean, I unfortunately didn't catch it on camera, but I did see diffusion policy do this task correctly one time, but it's very inconsistent and makes a lot of mistakes because it's trying to learn the human demonstration policy rather than separating what the human wants from what like the world is going to do. Yeah, this is just like, again, we saw this earlier. This is all of the human demonstrations we collected. But despite their noise, they have really valuable information, and it's worth extracting that information. So we should not limit ourselves to clean demonstrations, and we should look for approaches that, like a goat, can find nutrition in anything that is available. And what we're proposing is this model-based reinforcement learning system, Dreamer from demonstrations. But I think it's telling, like, that's not a perfect solution, because as I just showed, I only have results for diffusion policy, because diffusion policy trains much faster. And training an end-to-end model-based RL system in the world is so far very slow. So it's not that one should replace the other. It's just that model-based reinforcement learning can be used as sort of a good baseline to compare to imitation learning methods, and they both have things to offer. So, right, I think I covered these conclusions. Thanks so much for having me on, and thanks to my co-authors, Elaine, Shivam, Yash, Hong, and Haley, and I'm happy to take any questions. Cool. Why is there so much variance? How could we improve on stability? Variance, sorry, I didn't see when you asked this question. Variance on performance. Well, there's less variance with a converged reinforcement learning model. The imitation learning methods provide there's an output distribution. Okay, so for Gale and, for VMail and implicit behavior cloning, they give, Gale is producing a good demonstration or a good sample that comes from the demonstration distribution, and implicit behavior cloning is like sort of doing a probabilistic sampling, but those both are coming from the human distribution. So like they don't even know what a mistake in a human distribution is. Diffusion policy handles that a little bit better, because diffusion policy is actually trying to learn like an energy gradient, which my understanding of that, which is not perfect, is that it gets you away from problems of normalizing your output activations as a probability distribution and sampling from it. So it does consistently what it does, I guess is a way to say it. But if the input set of demonstrations doesn't allow it to be perfect, it will have problems. If you're talking about like the spikiness of those graphs, that was because to match up that data in a fair way, I basically just had to take the training performance as it went, which is more random and spikier. But like they still hit the same asymptotic performances. Yeah, I'm not sure. Let me know if there's a follow-up question that I can clarify. Yeah, I mean, so this question is sort of like, what is the deal with exploration versus exploitation using human demonstration methods? Human, the thing is like you could use human data demonstrations to do exploration too. Because you can be in a communication with the person that's giving the demonstrations. It's like one reason that human robot interaction and human computer interaction are so interesting is because there's so much information and knowledge and like expertise coming from even a naive human when you're talking about doing robot interaction tasks, right? Like, so one way you can go with AI is you can say like we're trying to make super intelligence do science, but in robotics, a lot of the time, even being like pretty good is good enough, as long as you're not breaking things and as long as you're not dangerous. And so humans have a lot to offer a robot learning how to do things. Like, one way that I speed up training when I'm allowed to be a participant is I just drive the robot into parts of the state space that I don't want it to explore. So like I'll spend maybe an hour with a controller just like sending the arm into corners, doing weird turns, because there's no reward up there. And I want the model to know that there's no reward up there, so that like I'm basically doing some of the exploration for it. That's also another reason why I mentioned like random walks earlier as a way to create data. That's like a really valid thing you could do for Model 2 is you can send the robot into every part of the environment that you know is not going to be a problem for it to like mess around in, you know, where it won't knock a shelf off a table or break a can. And then all that data can be sitting there as examples of parts of the state action space that don't have reward, which is useful for learning. Knowing where not to go is helpful. I'm not sure if that answers your question. Cool. Yeah, I'm happy to take any more. Thanks a lot. Yeah.
I just have a follow-up question. You were talking about sparse reward setting, right?
Yeah.
So I mean, like, why specifically you were trying to address sparse reward setting? Because, um, I mean, imitation learning is all about learning on expert demonstrations, right? So demonstrations are not like you don't generally have the reward function, right? You just have state action, state action. I mean, state action, next state action, you know, next
Yeah.
state, right?
Right.
So I don't really care about whether it's a reward, I mean, sparse reward setting or I mean, dense reward setting, right?
Yeah.
Should I?
Right. No, for imitation, you're totally right. For imitation and learning from demonstration, reward doesn't even come into play. So sparse versus dense reward doesn't matter. But when we bring in a model-based learner, which is a reinforcement learner, one is that, you know, it's sort of like it's sort of a hard thing to compare these two approaches because they have really different requirements in terms of data and time. But since we decided that that was a useful thing to do, one thing that sparse reward does is it makes that comparison more fair because the reward function is a lot of information about what should happen in the environment. Um, and so that's like one reason to do that is to say like we want this comparison to be as fair as possible. We don't want to give all this extra information. We're really, you know, for these tasks, there's some ways you can do it sort of automated with, like the push T task, you could just say that coverage is reward. That's the way to do it. But for the shelf restocking task and even for pin pad, you have to go in and say like, all right, well, you got two of the combos, so you get some reward. Or with the shelf restocking task, you have to say, well, here's some reward for grabbing the can, here's some reward for picking it up, here's some reward for putting it on the shelf, and here's some more reward for sliding it, which is really like a lot of additional invisible work that is not just here's the demonstration, which is like what we're interested in looking at. So that's one answer is sort of like for validity. And then the other answer is that I think I just, you know, this is just sort of my personal opinion, which is that reward functions, if you can operate without reward functions or with just sparse reward, it sort of simplifies learning. Like it's not that it's easier to learn without reward functions, of course not. But if you're combining reinforcement learning with demonstrations, and you're in these tasks that have definable goal states, so you know it's maybe a different thing if you're trying to learn a locomotion policy for like robot legs, where like they want to be upright and moving. You sort of have these like obvious continuous rewards you want to give them. If I'm saying I want this robot to make me tea, then by combining demonstrations with sparse reward, I give the system enough information to do like the value function estimation over time, right? Because like it doesn't have to explore randomly for 10,000 years to accidentally make tea. I showed it how to make tea. It sees the sparse reward in that. And now as it goes through its replay buffer, it can sort of back propagate the reward through time using temporal difference learning or whatever your approach is. And so, yeah, that's sort of like, that's the second part is sort of just like I'm personally interested in the combo of sparse reward and demonstrations because they they kind of help you get around the fundamental problem of sparse reward, which is that you are never going to find it with random exploration or even I mean entropy-based exploration, like with soft actor critic, that does amazing things sometimes. So I'm not going to say you're never going to find it there, but it
What
speeds it up
about
a lot. Yeah.
yeah, sorry for interrupting. Go
No,
on.
no, absolutely not. I'm sorry for rambling. Please go on.
No, that's fine. I mean, I just wanted to add, something to it. As you said, sparse reward setting, right?
Mhm.
If it's a sparse reward setting, there are methods like you don't have to literally give external rewards, right? There are methods which are based on curiosity, intrinsic motivation in sparse reward setting, right? They actually
Totally.
try to solve hard, uh, exploration problems, right?
Right.
I mean, would that help in this context?
Yeah, that's a good point. I mean, there's a entropy reward as part of
SAC.
yeah, which as part of SAC, and I think that it's in the Dreamer continuous action agent also, which is not, it's not necessarily formulated the same way as like some of the curiosity or intrinsic motivation approaches, but it definitely does help, and that's a great point. That that those are much more like hands-off, denser reward densifications. Yeah,
Mhm.
and like you can see even, one reason. So for, let's go all the way back to PinPad 5. One reason that the training window is set at 400,000 steps here is so that pure dreamer can get into the reward space. And that is the effect
Mhm.
of one of these intrinsic motivation rewards. Like I'm pretty sure that's just an entropy reward. Um, and it's effective enough that like eventually you get, by trying to explore as many states as you can in this like totally observable, small, discrete environment, you get to the point where you find the correct combination on a regular basis. Even if this is only 50% of trials, that's pretty good because like getting the right combo for 5 is hard. Uh, and when you step on the wrong, just a reminder of the environment, if you step on the wrong pad, your combination resets. So like doing this randomly is very unlikely. Um, and the intrinsic, it's not intrinsic motivation. I mean, I guess it's a version of intrinsic motivation, but the entropy reward here is enough to find something that hard to find with even like, I think this is 12 or 24 hours. Let me see if I've written down anywhere. On like a 3080 Ti GPU. But the nice, like, even so, that will get you there eventually. A nice thing about the demonstrations here, and this result is what initially prompted our interest in this, was how stark this was. When you give it demonstrations, it can find that solution because it knows that it exists. It'll learn a policy that finds it like in 3 hours. So that's kind of why we're interested in that area. But that is a totally valid point, and you're right.
Great. I mean, thanks for answering. I like your energy.
Thanks. Have you tried to present demonstrations in the middle of training as a means to guide it to another behavior than the actual? Yeah, I mean, that would work. Like, it still is going to end up operating. So if we're talking about Dreamer for demonstration, it will still end up operating on the basis of its reward. Its one-step reward prediction, like the world model's one-step reward prediction. So if you change where reward is coming from partway through, you'll have like this big error spike, and it will take a little while to recover. But if you're just going to add another state that also has reward, that would almost certainly be fine. So and maybe that's great because like you've already done all this learning towards your first reward, and you can probably leverage a bunch of that. Yeah, yeah. I haven't actually tried that though, but that's a good idea to do something like that.
All right. It was a really nice session. So, I mean, there's so many things which I would like to ask. I mean, I would be really interested to know more about your work. We can take it offline. In the interest of time, um, you know, we can take questions offline, or you can just like whoever is interested in having or ask some questions. Like, you can actually drop him a mail. I think your mail ID is shared with the community, right? I mean,
Cool, I think so. Yeah, my Tufts ID. I'll put it in the chat too what my Tufts email is.
right. Yeah, thanks, James. I mean, it's wonderful. I mean, I would definitely try to reach out to you offline. I'm Rahul,
Yeah.
by the way.
Nice.
I mean, yeah,
Nice to meet you.
I'm the one.
Are you
Yeah,
R4
yeah.
or N4? Yeah.
Yeah. I'm Marfa.
Cool.
Yeah.
Yeah.
Right.
Yeah. Thanks for inviting me.
Yeah.
It's good to connect.
Yeah, it's great to have you. I mean, yeah, I really appreciate your energy. I mean, I mean, I really like it because I mean, it's not that you were rambling. I really appreciate you're putting a lot of effort to actually explain it in detail, right?
Thanks. Yeah. It's always a decision about how much you go by like a predefined script and how much you like try to get into what is like actively interesting in the moment.
Mm-hmm.
Yeah. I've actually only done this talk one other time. So it's also like there definitely is some rambling. There's for sure some rambling.
No, it's pretty okay. I mean, like that's pretty great. I mean, I really appreciate it. I really enjoyed it.
Thanks a lot.
I would say I would actually invite you a little more times if you're interested.
Yeah, let me do some other work first.
Yeah, sure. Yeah. I mean, yeah, sure. I mean, in future, sure.
Yeah. Thanks.
Great.
Cool. Thanks a lot.
Yeah.
Thanks everybody.
All right.
Bye.
Thank you, James. Thanks everyone for joining. All right. See you guys.